Marlowe contracts are fundamentally data structures that can be represented in various languages. While Haskell is the native language, Marlowe contracts can also be written in JavaScript or TypeScript, making them accessible to web developers. The TypeScript library for Marlowe provides a familiar syntax for creating financial smart contracts. You can try this directly in the Marlowe playground by selecting Start in JavaScript on the home page or by opening one of the JavaScript examples. The playground provides a complete environment where you can write, compile, and simulate your contracts. The TypeScript embedding mirrors the structure of Marlowe itself. For each Marlowe type in Haskell, there's a corresponding TypeScript type, and for each constructor, there's either a constant or a function definition, depending on whether the constructor takes arguments. Let's explore how this embedding works and build a practical financial contract step by step. When you open the JavaScript editor in the Marlowe playground, you'll notice import statements at the top of the file. These import all the Marlowe constructs you'll need, such as contract, value, observation, and more. Some Marlowe constructs don't have arguments and are represented as constants. For example, time-interval start is simply a constant that represents the start of a time interval. Other constructs like available money take arguments and are represented as functions. The beauty of this interface is that you don't need to work directly with JSON or understand the internal representation. The TypeScript type system ensures that when you use these functions correctly, you'll produce a valid Marlowe contract. To create a contract, you write code inside the provided function body, construct your contract using the Marlowe building blocks, and return it. When you click Compile, the playground executes your code and converts the returned object into a Marlowe contract. A key consideration when working with financial contracts is number precision. JavaScript's native number type uses floating point representation, which can lose precision with large integers. Consider that in JavaScript, 9007199254740992 equals 9007199254740993, clearly problematic for financial applications. To address this, the Marlowe JavaScript library supports 3 ways to represent numbers. Native numbers are simple to write and work with standard operators, but they lose precision for large amounts. String representation preserves precision for large numbers, but doesn't work with standard operators. For example, 32 plus 57 would result in 3257 rather than 89. The recommended approach is using JavaScript's Bigint type, written with an n suffix like 1000n. This gives you both precision and the ability to use standard operators. All these representations are converted to big number internally, but precision loss may occur if you use native numbers. The Marlowe JavaScript library provides some convenient shortcuts. In Haskell, you would use trueUbs and falseUbs for Boolean observations, but in JavaScript you can simply use native true and false values. Similarly, where Haskell requires a value type, the JavaScript library accepts an eValue, which can be either a number-like value or a proper value object. This makes your code cleaner and more natural to write. For example, instead of writing constant 5, you can simply write 5n. These shortcuts maintain type safety while making your code more readable. The library also allows you to define custom types to organize your contract logic. This is particularly useful for complex contracts where you might want to group related data together, such as information about parties in a transaction. These features make the JavaScript embedding particularly approachable for developers coming from web development backgrounds. Let's walk through creating a swap contract where Alice exchanges 50 ADA for 100 fiat dollars with Bob. First, we define our amounts. Since Cardano works with Lovelace, 1 millionth ADA, we calculate 50 ADA equals 50 million Lovelace. The dollar amount is simply $100. We then define each party's information: who they are, which currency they're offering, and how much. For Alice, it's the Alice roll, ADA currency, and X Lovelace. For Bob, it's the Bob roll, a dollar token, and 100 units. With the parties defined, we structure the contract as a sequence of actions. Alice deposits her ADA, then Bob deposits his dollars, followed by Alice's deposit being paid to Bob and Bob's deposit being paid to Alice. For each step, we specify a timeout and what happens if the step isn't completed, typically refunding any prior deposits. To make our contract cleaner and more modular, we can create helper functions. We might define a makeDeposit function that handles waiting for a party to deposit their currency, and a makePayment function that transfers currency from one party to another. These functions take parameters like who's depositing, what they're depositing, timeout information, and what happens next. They return Marlowe contract fragments that can be combined to form the complete contract. The final contract is then constructed by chaining these function calls together in the correct sequence. Alice deposits, then Bob deposits, then payments flow both ways, and finally the contract closes. This approach makes complex contracts more manageable and easier to understand. It also allows for reusing common patterns across different contracts. After writing your contract, clicking Compile in the playground converts it to a form that can be simulated. After building the contract, it's essential to test it thoroughly. This allows you to step through the contract execution and see how it responds to different inputs and timeouts. In the simulator, you can make deposits as different parties, choose options when the contract presents them advance time to trigger timeouts, see how funds move between accounts. Testing helps identify logic errors or unintended consequences before deploying to the blockchain. Pay special attention to timeout scenarios. What happens if one party fails to act within the specified time? Once you're satisfied with your contract's behavior, you can export it from the playground for deployment on the Cardano network. The playground provides JSON output that can be used with the Marlowe runtime or other deployment tools. Remember that on the blockchain, deployed contracts can't be modified. Testing thoroughly beforehand is critical to ensure your contract works exactly as intended in all scenarios.